So welcome everyone. Thank you for being here. Before I start, I would like to thank all the members of the jury for the reviews, for the time and the effort reviewing my thesis. So the project that my PhD was funded by European Union Horizon 2020, specifically by SPIN in the framework of SPIN-ITN program, which also I thank all the people that were in the organization. So today I'm going to present the work of my PhD, in which I investigate the scattering of seismic waves in heterogeneous media. So I would like to start by saying that the analysis of seismic wave is the most important tool that we have to investigate the Earth interior. As analyzing seismic waves, it is possible to get a deep understanding of the Earth structure, its dynamics, and the physical processes that are happening inside the Earth. The reason why we can use seismic waves is that as seismic waves are propagating inside the Earth or propagating medium, their propagation is shaped by the elastic and inelastic properties of the medium itself. More specifically, their propagation is governed by the wave equation. At any observation point, we will observe a signal which is composed by two contributions if we neglect the instrumental response, which is one contribution is related to the source that generates the signal, and another contribution is related to the propagation waves between the source and the receiver. Now, the simplest medium that we can imagine is the so-called homogeneous medium, which is a medium in which the elastic and inelastic properties are constant in space. In this case, we may be even able to solve the wave equation to retrieve an analytical solution, which will tell us that the paths of the waves are straight lines between source and receiver. However, an homogeneous medium is not a very good representation of the complex subsurface. Indeed, we are expecting that there may be different kind of rock types, presence of fluid, fractures. All these features and many others may generate variation in the physical properties of the medium. So if we now add this complexity to the medium, what we will observe is that waves are interacting with such heterogeneities, and they will change their propagation direction as they interact with them, their phase, and as well amplitude. This complex phenomenon is called scattering of seismic waves. Under scattering condition, even if, for instance, we consider a source function that is simple as the one that we see, what we can observe is something that may be very complicated. What we can say is that the signal that we observe is first much longer than the source function that generated, and also is composed by multiple arrivals. And this is due to the fact that as waves are propagating in a heterogeneous medium, they may propagate along different direction and get to the same observation point at different time lapse. So this signal is very complex and seems also chaotic, but it's very important to understand that actually all the information about wave-medium interaction is encoded in this recorded signal, which means that it is possible to analyze this signal to infer properties of the propagating medium or of the source. Just to show some applications, because the scattering of seismic waves has been used in many applications to constrain the properties of the medium. In 2022, Mao showed that it is possible to monitor groundwater reservoir, or for instance, another application could be volcano monitoring or imaging, which it's something that is important also for the safety of the population. Or just to show another example, it is possible to run geothermal site investigation. So those are just some examples of the many that I could have done to show how we can use seismic waves to constrain the properties of the medium. But in this broad context, our objective is the following. We want to enhance the interpretation of seismic signal that have been propagating complex media to resolve source characteristics and subsurface, to better resolve source characteristics and subsurface properties. We will do this by using two tools. The first tool is the scattering theory, mainly radiative transfer equation, and then also we will perform many numerical simulation of the wave equation. In some studies, we will also use the so-called new observable of seismology, which are the Wavefield gradients, and as we will see, they are the rotation and the linear strain. So before I will present the tool, so just one last remark. I would like to show how it looks a medium which is more representative of the what we are expecting to see in the subsurface, because what I showed before was a very schematic representation. But if we want to imagine something that is closer to actual real condition, we should imagine something that looks like this, in which, as we can see, the elastic parameters are continuous, and the variation of elastic parameters is continuous, and no isolated scatterers can be easily identified, for instance, in comparison with before, in contrast with before. So the first tool that we have is the scattering theory and radiative transfer equation. In this case, scattering theory provides a statistical framework to study the scattering that treats the scattering not as a deterministic phenomenon, but as a stochastic phenomenon. The key idea, which is behind the scattering theory and radiative transfer equation, is that we can extract some statistical properties from the propagating medium, as, for instance, the typical shape of the heterogeneities, which are defined by the correlation function, the size distribution of the heterogeneities, which is defined by the correlation length, and then the distribution of impedance contracts between background medium and heterogeneity, the so-called amplitude fluctuation. The idea is that if we have this information about the medium, then we can have a description of the scattering process that is happening inside this medium. But it's easy to understand that actually those properties do not describe a unique medium, but actually they describe many media will satisfy those properties. And indeed, this is a very important key point of scattering theory radiative transfer equation, which is the fact that they don't provide information about the propagation in one medium, but actually in an ensemble of media, which share the same scattering characteristics. And for instance, here I'm showing a very small ensemble in which I realize 9 media, which share the same scattering characteristics, but actually, if we look carefully, the position of the heterogeneities is changes from medium to medium. So central to the scattering theory, there is the radiative transfer equation, which is an equation for the average specific intensity and describe the process of scattering from the single to the diffusive regime. As we said before, if there are no heterogeneities, the paths that we are expecting to see are straight lines. But then if we consider heterogeneities, if we introduce heterogeneities, then scattering will occur. In this case, this equation is telling us that if we want to, the intensity that we will read at a specific distance from the source at a certain time, a certain frequency range, if we choose a reference beam of waves propagating in one direction, is given to the source, so the energy that we input in the system, is given to the fact that part of the energy is actually lost by the fact that by interaction with heterogeneity, some energy can be scattered in other direction. And then also that part of the energy will be gained by the fact that the neighborhooding beams may scatter energy along the direction of propagation of our reference beam. In this study, this equation was solved using Monte Carlo methods in elasticity, considering the coupling of P and S waves. So now we have some insight about the scattering theory and the radiative transfer equation. We can make some observation. The first observation I would like to make is that when we extracted the properties from the medium, actually we could consider only some distribution in order to compute the scattering parameters. Then, as I highlighted, RT provides an average response of an ensemble of media, which is different from what we would observe in field conditions, because we observe waves that have been propagating in one medium. And then again, it provides an information for the specific intensity, which again is different from the ground motion, which we generally observe. So another way to address the scattering problem is to solve the wave equation. To solve the wave equation, we need again to define our medium, but in this case, we need to define the elastic properties in each point of the space, but they can also not exhibit any specific correlation. And also we can consider, for instance, sharp changes, which means we can introduce interfaces. Also, as we will see in this thesis, scattering properties can quickly change spatially. So in this study, the wave equation was solved using spectral element methods, which is probably nowadays the most used method to ease computational velocity of computation and accuracy. And here we see on the right one example of one of the computation that we will analyze later in this presentation. So now we have an idea about the tools that we use to investigate the scattering properties. Just to remind, so the objective is to enhance the interpretation of seismic signals that have been propagating in such complex and heterogeneous media to better resolve source characteristics and subsurface properties. Then now we can take a look at the investigation outline. First, we will start our study by studying the scattering process in a homogeneous or weakly heterogeneous media containing a single strong subsurface anomaly. Then we will move to a more complex system. We will analyze the scattering process in a uniform heterogeneous media, which is a media defined by the fact that the scattering properties are constant in do not change in space. And then in the third part of this thesis, we will analyze the scattering process in non-uniform heterogeneous media. Specifically, in that case, we will analyze the scattering process in a volcanic plumbing system. Now, so let's start with the first project. In this first part of the thesis, we analyze the single scattering regime. So to have just a simple idea about the single scattering regime, the single scattering regime is that portion of the wave field which is considered being dominated by waves that have interacted only with one heterogeneity. So if we consider this schematic representation in our seismogram, the first waves that we will read are the ballistic waves, and after that we will see the transition to single scattering regime. Now, in this first study, what we would like to do is to study the sensitivity of to characterize the sensitivity of the seismic wave field gradient. As wave field gradient, we define the rotation and the strain, which are two observables that can be obtained by linear combination of the gradients of the displacement field. These observables can be recorded using some instruments, so rotational sensors in case of the rotation, which are optical gyroscope, and then distribute acoustic sensing in case of linear strain, which is an instrument that used to compute the deformation on a fiber optic cable. So the reason why we want to introduce these observables in this context is the following. First is due to the fact that, especially if we talk about dust, has generated a substantial amount of data. If we look, for instance, at the scientific production in the last years, we see that there is a huge increase. This is due to two reasons. First is that it offers high density measurements, and also to the fact that it is very easy to deploy in difficult environments. There are many applications, for instance, in volcanic environments or even in urban environments. The second reason which we decided to include the wave field gradient is the fact that it is shown many times that they are highly sensitive to shallow heterogeneities. Some studies also in the past characterize some aspects of this sensitivity. And what we want to do at this point in this context is to characterize gradient sensitivity to shallow heterogeneity and test their applicability for the detection of strong subsurface anomalies. We will do this, we did this by dividing the study in two parts. First, we theoretically characterize the sensitivity considering a very simple model, a plane wave propagating in one direction, interacting with a scatterer that was defined by a direct delta. In this case, by analyzing the amplitude of the displacement and the gradient field, we were able to show that the gradient field has a higher amplitude in proximity of the scatterer. So using these findings, we then provide a method, which we called proximity field test, or PFT. This method is a method that combines gradient, one component of the gradient, and one component of the velocity field. We show that it allows to partially isolate the scattered field, and its amplitude can be used as a proxy for the detection of strong scatterers. So using the findings of this theoretical characterization and this method, we then validate these findings in first numerical simulation of the wave equation, and then we also performed a field experiment. I'm showing here the very schematic representation of the field experiment, in which there was a varied heterogeneity made of concrete in the shallow subsoil. We deployed receivers at the free surface, dust and geophones, and then we produce waves with an active source. What I would like to show is that when we look at the section of the horizontal acceleration and strain, even if this heterogeneity generated a very strong impedance contrast, actually no clear signature of the heterogeneity is visible. But at the same time, when we look at we analyze the data with the proximity field test, we show that even if we use data only from geophones or data only from dust, we see a clear signature of the heterogeneity in the very proximity of it. So in this case, we conclude saying that the wave field gradient have an increased sensitivity, which we partially characterize, and then also that PFT can be used efficiently to detect strong anomalies. It's interesting to see that it works even when we use only dust data, which open in future for future application, in which it could be possible to use it in environment in which only dust data is available. So with this observation, I conclude the first part of this thesis. I would like, so now we start with analyzing the process of the uniform heterogeneous media. And in this case, we analyze the full scattering process. So if we take again the seismogram that we saw before, we are expecting that after the single scattering regime, we will get to the multiple scattering regime, which is a regime in which waves are considered to have interacted with many heterogeneities, and it was also the regime in which the seismic coda emerge. After that regime, we will get eventually to the diffusive regime, in which the wave field is considered to propagate according to the diffusion equation, so as a smooth flux of energy. Now, our investigation of the scattering process in this context starts from a reliability assessment. In this case, what we want to understand is if our numerical simulation are able to completely replicate the propagation of seismic waves in heterogeneous media, according to the theory. So there are many studies in the past that have addressed the issue of reliability, considering multiple or single aspects of wave propagation, considering different kinds of solvers, or even 2D or as well 3D medium. In this context, our contribution wants to be the following. We want to offer an evaluation of the reliability of 3D spectral element simulation by comparison with the theory in both full and half space media. So we will do this by analyzing three aspects: scattering mean free path, the transition between multiple scattering to diffusive regime, and P2S ratio evolution. Before we will analyze these aspects, I will just would like to give a look about the medium that we analyzed. So this medium was characterized by heterogeneities which were correlated considering a von Karman autocorrelation function with a correlation length of 320 meters. And we explored three levels of velocity fluctuation between 10 and 25%. Then in the results that I will show today, which will only concern the full space simulation, we consider this source to receiver configuration. The source is at the center of the medium, expressed by an isotropic moment tensor, and then we deployed the receiver on spherical shells at a different distance from the source. This symmetrical configuration was required in order to compute the average energy and to be able to compare it with the solution of the radiative transfer equation. So starting from the first analysis, we looked at we analyzed the scattering mean free path, which is the average distance between two consecutive wave heterogeneity interaction. In this case, the 10% heterogeneity velocity fluctuation case, I'm showing the radial mean field on the left, which is the average of the radial component of the displacement at increasing distance. And then by fitting the decay of the frequency component of the radial mean field, we were able to compute the scattering mean free path, which we then compared with the theory, showing that there is a good agreement at least between 1.5 and about 3 Hertz. Now, when we increase the level of fluctuation to 25%, the first thing that we can observe is the fact that we introduce more scattering. And indeed, the average is not able to remove, to suppress all the fluctuations as before. And then part of these fluctuations are also appear in the computation of our scattering mean free path. We see larger error abundance, also some fluctuation. Nevertheless, we see a good agreement between about 0.8 Hertz and 2.5, 2.6 Hertz. It's interesting also to notice that in this case, since we increase the level of fluctuation, the scattering mean free path decreases compared to before. This means also the dynamic of velocity of transition between scattering regime is accelerated. And indeed, this is exactly what we find when we look at the transition between multiple scattering regime and diffusive regime. In this case, we analyze the energy evolution of the three observables of the displacement, the strain, and the rotation at 5 kilometers distance from the source. And we see that they fit very well the decay that is expected from the diffusion equation in the 10% case at about 12 seconds, and in the 25% case at about 6-7 seconds. So this shows that the dynamic is accelerated. Then we analyze the P2S ratio, energy ratio, which is an evolution that which evolution is given by the fact that as waves propagate in heterogeneous medium, the phase gets converted from P2S and S to P in a full space medium, and this dynamic is governed by the mean free paths. So we observe that we have very good agreement in the 10% and as well 25% case. It's interesting to see that the dynamic is accelerated in 25% case, so we even reach the asymptotic limit, which in this case is not given by the scattering mean free path, but the elastic properties of the medium. So the same analysis that we did in the full space medium were also performed in the half space medium, showing that there is a good agreement with the theory. So in this case, we can conclude that at least in the limits that we tested, spectral element simulation accurately model the propagation of seismic waves in heterogeneous media. And this means that the simulation are a reliable tool to study the scattering process. Now, before we will move to the non-uniform heterogeneous medium, I would like just to show some another observation, which is the fact that when we analyze the energy of the average energy of the three components, radial and two transverse, of the displacement, strain, and rotation at increasing distance from the source. What we observe in this case is that the dynamic seems to be partially different. For instance, in the displacement field, we observe that depolarization, which is the phenomenon in which the energy envelope of the three components overlaps, occurs after the arrival of S waves. Same we can say for the strain, but if we look at the rotation, we notice something different. What we notice is that the radial component, which point to the isotropic source, is less energetic and takes more time to depolarize. If we want to be quantitative, if we consider the scattering mean free time, which is the average time between two consecutive wave heterogeneity interaction, this is about 1 second. So this means that this depolarization doesn't occur for at least 10 to 15 mean free paths times. It's important to highlight also that between all this observable, rotation is the only one which is sensitive only to the S field. So in conclusion of this study, we can say that the S field evolves differently from the P field, as source information seems still to be visible at 10 to 15 mean free times, and also that in the displacement field and in the strain field, this contribution could be hidden by the fact that actually in that case we see both contribution of the P and S field. This means also that rotational measurement could be used to get to constrain better the source polarization and the propagation direction. So now we will move to the third study. In this case, I analyze a non-uniform heterogeneous medium. In particular, we will look at the scattering process in a volcanic plumbing system. In this case, the model that we used is a model that was derived by thermoelastic simulation for injection of the dikes and seals without eruption. We took one of the frame of this simulation and we transform it in a velocity model that we see on the right. The model that we see in this case is much more complex than the model that we analyzed before. And the reason is that it belongs to the family or category of the non-uniform heterogeneous model, which means that the scattering parameters are changing depending on the region that we are observing. And for instance, I'm showing the velocity fluctuation on the right, in which we can see that the range of is between 0 to 0.5, and also the horizontal correlation length, which to make a comparison with before, it was set to 320 meters. In this case, changed from few tens of meters to even kilometers. So this model, this highlights the fact that this model is much more complex than before. The reason why we wanted to study the propagation of waves in this model is not only because we may like very complex model, but is also due to the fact that we would like to focus on a specific signal, which often has been observed in inactive volcano system, which is the long period signal. These signals are characterized by low frequency, below 5 Hertz. And what I would like to show in this case is the fact that these phenomena are very complicated. And in the last 40 years, many authors provide different models to propose different models to explain the origin of such a signal. So this won't just to highlight the complexity which is behind this signal. But in this case, what we want to do is not to provide an additional model, but we would like to focus on a specific feature, which often has been observed in many of the studies that I cited before, which is the fact that some frequency component seems to be stable over time. I'm showing, so on the right, an example of a volcanic long period signal. Then we can see the spectrum in the center panel. We see that there are some clear peaks, and then the spectrum is in the bottom panel. Then on the right, I'm showing a full network analysis from Barajas, in which it is shown that at least for some days there is a spectral consistency of some spectral components. Now, this stability is often interpreted as being related to the source, but in this case, we want to understand if it is possible that this stability may be generated by the scattering of seismic waves within the volcanic plumbing system. So the way we did that is to perform many numerical simulation of the wave equation. In this case, we considered 5 receivers at the free surface and about 8,000 receivers at depth. We used the reciprocity theorem that allows us to exchange the position of source and receiver, and indeed in this way we were able to achieve this configuration just by running 10 simulations for a total of 50 days, instead of about a century that would have been required if we would not have used reciprocal conditions. So, before we will move now to the analysis of the simulation, I would like just to make some more observation about this model. And it's the fact that we say that this model is very complicated, but actually this model may be even be more complicated. We could have considered, for instance, absorption, which we know that is present in volcanic environments and is really strong in the shallow layers, or we could have considered topography, which is something that many authors also show that is very important as it shapes strongly the signal that we actually observe in real field condition. But the focus here is to understand if the structure by itself is able to generate stable peaks in the spectrum. So this is let's say a final observation. Now we can move to the simulation in reciprocal condition. So the source is at the free surface. Then we see waves propagating in the lower part of the medium, Rayleigh waves propagating on the right. And then we can see that a lot of scattering is produced in the deep part of the model, which is the part between the region between about 8 to 12 kilometers depth, characterized by very high velocity fluctuation and low average velocity. So the first analysis that we did in this case is to look at the signal and its spectra generated by several sources observed at one of the receiver at the free surface. What we observe is that as we move the source deep in the structure, the seismic coda increases. And also what is interesting to see is that even if we consider the source number 1, which is located in an area which is homogeneous of the model, actually what we observe, the spectra that we observe is already very complicated. It shows many peaks while the source function is, for instance, very smooth. So at this point, we want to understand if the complexity of this signal is coming from the ballistic part or the scattering of waves. So the analysis that we did is the following. We consider one receiver at the free surface, vertical displacement in this case, and we consider all the signal that we observed at the 8,000 receiver, 7,800 receivers. We split the signal into parts, part that is the ballistic part, and then the coda, and we analyze separately their spectra. What we observe in this case is that the spectra of the coda appears to be much more complex than, and we see many spectral lines compared to the one of ballistic waves. So this means that much of the complexity that we observe is due to the scattering process. So at this point, we want to understand how sources located in different areas of the model are able to trigger different frequency. And to do this analysis, we looked at the average energy of the coda observed at the 5 receivers at the free surface for each one of the source. What is interesting to see is that there are some sources located in some areas are generating scattering in a wide frequency range between 1 to 8 Hertz, for instance. That is the range that we investigate. But then sources located in other areas, for example, the area number 2, show scattering mostly at high frequency, while, for example, in area number 3, mostly at frequency between 3 to 4, in the range of 3 to 4 Hertz. So this means that in this complex medium, different sources located in different areas are able to generate scattering in different frequency ranges. But in this case, we are still looking at some frequency range of 1 Hertz. We would like at this point to look at directly at the spectral peaks. So we did this analysis in which we consider two sources, one located in the deep structure of the model and one at about 8 kilometers. And we analyzed the spectra that we observed at the 5 receivers. We looked at the full spectra and then the spectra of the late coda. I'm showing in this case the spectra of the receiver number 3 in black, and then of the average in red, and the other receivers in light gray. The first observation that we can do is the fact that it seems that there are a lot of peaks. Now, these peaks are maybe generated by two effects. The first is multipath arrival. So as we saw at the beginning, if you remember, we said at the beginning that waves may, in a heterogeneous medium, they propagate along different directions and they can get to the same observation point, generating also an interference in the frequency domain. So in that case, the peak that we will see is a peak that is related to the specific path between source and receiver. And this means that it will appear at one of the observation point, but it may not appear at the other observation point or in the average spectrum, as for example, the ones that I'm showing. And then there are other peaks, for example, the one that we see very clearly in the late coda, which seems to be independent on the observation position. So this means that potentially this peak may be related to some sort of trapped waves or resonances. So we would like now to understand a little bit better what generates this peak. And the way we did that is to consider the following configuration. So not in reciprocal condition. In this case, we filtered out signal between 1.5 to 2.5 Hertz. We considered one source at the free surface, and then we looked at the displacement along the vertical profile. The idea here is that this vertical profile will behave as a vibrating string excited by the source at the free surface. And this means that we may be able to see two effects. The first is that if there are traveling waves, when we look at the time overlaps, we will see something that looks like this. But if there are standing waves, then in time overlap, we would observe something that looks like this, in which there are points, there would appear points of node displacement, the so-called node. So when we do this analysis, we see that at the very beginning, waves are propagating in the lower part of the medium. And then as soon as the ballistic wave travel outside the region that we investigate, we start to see some nodes in the lower part of the medium, especially between about 9 kilometers to 10 kilometers. What is interesting to see is that these nodes, which indicate resonant waves, appear even at the very large time lapse, even at the last time step of our simulation. So our interpretation of this mechanism is that waves may be trapped in that region, in the deep region of the medium, because that region is characterized by low velocity, high velocity fluctuation, and also is surrounded by high velocity. This means that the contracts in elastic properties and in impedance contracts may generate trapped waves in this area, which is what we observe. In conclusion, what we can say is that it's interesting to see that in this condition, coda waves still contains information associated with trapped waves in the source area. But then on the stability of the spectral components of long period events, we can observe that peaks that appears at multiple receivers may be indicative of resonance within the volcanic structure. But this also means that since the volcanic environments are dynamic environments, this means that, for instance, changes in the structure may lead even to change in the resonant frequency. So before now we will move to the conclusion, I would like just to show another application in which the same synthetics of this study were used to compute the complexity of the signal and trying to relate this complexity to the source the scattering properties of the source area. So this study is a study that is made in collaboration with Reza Esfahani. The idea, the pipeline, is what we observe here. So we consider the 5 receivers at the free surface, the 2 components of the displacement generated by each source. We normalize these signals to remove source information, and then to put ourselves more close to real field condition. And then first we extract features using SCATNet, which is a 2-layer wavelet transform, Then we use the UMAP to reduce the dimensionality of this data and to plot them in a 2D space. And then we reduce the features of the SCATNet output to extract the minimum number of features, which we call the complexity index, that was necessary to explain what we observe in UMAP. So in this case, what we observe is that the complexity is very well correlated with the scattering strength of the signal and scattering properties of the source area. For instance, we see that it increases as the velocity fluctuation increases, and also that it increases as the correlation length of the source area decreases. So in conclusion of this study, we show that the complexity index can be used to analyze the seismogram and to infer scattering properties of the source area. This also opens for future application for real data. So now we will move to the conclusions. In the first part of this thesis, we analyze an homogeneous or weakly heterogeneous media containing a single strong subsurface anomaly. In this case, we have shown that the Wavefield gradients have an enhanced sensitivity to strong heterogeneities, which we characterize. And then we define the proximity field test, which defines a field which may be investigated more in depth as we investigate only some components. And then also it's interesting that for our application, the proximity field test is very efficient for the detection of strong anomalies in the subsurface. And is more interesting even the fact that actually it works even if we compute it only using DAS data. So this means that the DAS using the PFT method can be used for the detection of strong anomalies in environment where no other instrumentation is available, for instance. But this is also important if we want to use data for other DAS for other application. For instance, it could be important to perform this test because it may be important to know that close to our observation point, there may be a strong scatter that affects the signal that we observe. So moving to the second part of the conclusion, in the second part of the study, we analyze an heterogeneous media, uniform and non-uniform. The first thing that we show is that spectral element simulation of the wave equation can correctly model the scattering of seismic waves, which is a requirement to use the simulation to study the scattering process. And then what is interesting to see in this work is that we notice that in the uniform heterogeneous media, the S field seems to contain information in forms of polarization and propagation direction of the source, at least up to 10 to 15 mean-free times. And also in non-uniform strongly heterogeneous media, we show that standing waves may be generated in the source area, and they may appear in the spectra even at the larger time lapse. Just one last observation is the fact that if we would have used the radiative transfer equation, in this case, we would not have been able to reproduce the full dynamic, since, as we described before, first, it describes an average solution between media, and also doesn't account for the signal space, which is necessary to produce standing waves, and so resonance. So, in conclusion, we show that at least in the conditions that we test, source information can still be observed in the coda at large time lapse. This information can be used, which was our objective at the beginning, can be used to better constrain the properties of the source or of the propagating medium. And now I would like just to one quick slide on the perspectives, how to move forward. Let's say that we use RTE for the reliability assessment of spectral element simulation, but actually because of the fact that RTE is able to provide information about the propagation of waves in an ensemble of medium, it can be used for other application, for instance, for the computation of the coda sensitivity kernel, which are some functions that allow us to map the scattering properties and monitor temporal change in the medium. At this point, we think that it's important to test the radiative transfer equation, even considering, for example, free surface, including Rayleigh waves. and taking into account effect, which has been highlighted, for instance, in the paper that I'm showing here, the non-uniform scattering, which could be very important to build a sensitivity kernel, which could better constrain the properties of the propagating medium. In this case, for instance, and I will conclude, we show that the sensitivity changes a lot if we include some heterogeneities in some part of the medium. And so with this, I conclude. Just one last remark. Is that so at the moment we are I'm already start to work on this, that we are generating a synthetic data set with spectral LLM simulation, and the objective is to test the capability of RT kernels to imagine local changes at depth. And so this is the conclusion for real. So thank you for your attention.